This is part 13 in a series of videos in which I'm working on this. It's a reproduction of an ADM-3A dumb terminal main PCB. Very large PCB. It dates back in its design to the late 60s, early 70s, so a very old design, uses almost entirely discrete TTL components. And it's a very complex circuit, but a very interesting one. There is no microprocessor in this. As I say, it's all discrete. And I've been trying to reproduce it as faithfully as I can. Unfortunately, the schematics I have are not the best. They're quite difficult to follow, and there's a lot of errors on them. And also I had to modify the design a little bit to use modern EPROMs rather than the old mask ROMs, which you just can't get these days, and even if you could, they wouldn't be programmed. So I modified that part of the schematic, which is this, and in the last video I showed the output from the shift register that's taking data from the ROM. I'd already been through in previous videos all the system counters as far as I could, and the display counters, so we saw that there was something on the display. It was taking the basic information I put into the ROM, and it was displaying something on the screen. It wasn't displaying it properly because where we were tapping off the video signal, it hadn't gone through all the processing for the video, so it didn't include the cursor information or things like that. And also it looked very messy because the information for properly formatting the display and blanking it, etc., wasn't present. So I've now got all the counters installed that are used to drive those particular circuits, and before I power this up, we'll just have a quick look at why the circuit looked so messy before, or rather why the display looked so messy before. So what we had was the output from the ROM, and it comes out, and the particular pixel value, whether it's bright or dark, depends on where we are on the screen and where we are within the particular character that's being represented. So that comes out of the shift register, and it then goes off to be processed and to be mixed with other signals, and that includes information that comes from various counter circuits. And these other circuits are used to determine whether or not there's a cursor present, whether the signal needs to be blanked. So for example, this particular circuit is really a series of counters, so as data is entered into the memory, so the cursor position is incremented or decremented, it moves across the line in one direction or another, or up and down the screen, and the various counters that keep track of that are used in conjunction with the counters that scan the display, and when the two coincide, then the signal is inverted to produce the cursor. Also, because the same memory that generates the display data is also used for the serial data, and it's single port RAM, so you can't read and write it at the same time. So if you read the technical document in the service manual for this, it says strange things happen if you try and do that. So I was interested in what those strange things were. So I'll demonstrate that in a few minutes, and you'll see what the display looks like if you don't blank the display. But obviously for all this to work, all the counters and all the logic needs to be in place. And I did order some counter ICs, but they arrived damaged. I've now got some new ones, so I've fitted those. I've got most of the ICs fitted now. Haven't fitted the RAM yet. I'll come onto that in a future video. But what I've done here is, so I can properly test this, if you do decide to buy one of these boards and build one yourself, you don't need to go through this lengthy test procedure. I'm just doing this to make sure that I haven't messed up the design and made mistakes on the track. As I say, the schematics are very hard to follow, so I'm being very careful in the way I'm approaching this. And I'm trying to break it down into logical blocks as well. If you look at the overall schematic, I think there were 13 or 14 of these sheets, and if you look at the entire schematic as a single schematic, it looks very confusing. but when you break it down into logical blocks, it's quite easy to follow and understand. It's just there's a lot of interaction between the various parts. So to cut that interaction down, what I've done, I've popped out or left out this IC. So it's H1, and H1 is the IC that's responsible for really driving the end of line updates. So if you enter a character or do something like that, then the output from this device is used to allow that to propagate through the system. So by taking it out, you kind of run it in a static mode, although it's still all these scanning circuits and cursor generation circuits that are running. The system as a whole is kind of stalled by the fact it's not there, and you can also kind of half manually drive it as well. So we'll look at that in a few minutes, but just to show you where that is, this is one half of it. It's a dual 4 input NOR gate, and this is one half of it. It takes various signals and it generates what amounts to the cursor update, cursor increment signal. The other half of it is used on this part of the schematic, which is the keyboard, and it's used to action the character insertion into RAM. So when you press a key, then it's used here to shift that data into memory, because obviously when you press a key it has to be serialized. So that's what this part of the circuit does, and by removing this you stop this this serial data being generated. So I popped it out, and we've now got this running in static mode. I've been testing the various circuits. I haven't bored you with that. It's quite tedious, and as you can see, I've been fitting the discrete components as I've been going. So what we'll do now is power this up. I've got the video signal connected to this location, so we're looking much further forward in the video path than we were previously, and this should now include the cursor. So we've got the cursor generation interface and mixing here, as well as the data coming out of the ROM. We also have the video blanking. As I said, we can't read the memory and write it at the same time, so the video blanking is quite basic. When we select data from the ROM, then what we're actually doing is taking a value from RAM. So the RAM's laid out as a kind of matrix that represents values to be shown on the display, and these values are character values, and those character values are used to select bytes within the ROM that are used to construct the characters, and that's done through a couple of latches. So the value from RAM is put into the latches, and the output of those latches selects the appropriate data from the ROM. That goes into a shift register, and then it's shifted out into the video stream and mixed with the cursor data. So to blank the signal, we have this arrangement up here, and what essentially happens is when the system needs to read the RAM, or if it wants to blank the retrace, which is the point at which it reads the data, then it asserts a signal which it calls video blank, and all that does is it asserts the clear pins on the two latches, and that causes the latches to be cleared. But because of the requirements for the values for the character set, it doesn't clear all the bits to 0. If you look through this very carefully, and I'll get the other part of the older schematic so we can see this more clearly. So this is the original schematic, and this part of it is actually the same. So when we look at this, we'll see that CBuff1 up through CBuff7 are the character buffer lines. LC0 to LC2 are the character line selections. So each character is made up of 8 bytes, and that's what these 3 lines select. And the actual character block within the ROM is selected by the CBuff1 to CBuff7 signals. But if we look through these, we'll see that a CBUF1 is the C0 output of this device, CBUF2 is B0, CBUF3 A0, CBUF4 D0, CBUF5 is A0, but CBUF6 is actual not B0. In other words, this is the inverted output from this buffer, and then CBUF7 is the D0 signal, and the other output's not used, it's just the 7 bits. And what this means is that when we clear these two latches, we end up with a value on these pins of 0, 0, 0, 0, 0, 1 zeros. In other words, we've got a 1 here rather than a 0 when we clear these two latches, because we're using the inverted output. And we also take into account the lower 3 bits, then that gives us a value of 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. And if you work that out, that's 100 hex. And if we look into the character set for the ROM, you'll see that at 100 hex we have the space character. In other words, all the values are 0. So the way the blanking works is when we want to blank a portion of the screen, if you assert the clear on these two latches, it selects one of the bytes within the blank character, doesn't matter which one because they're all 0, and that means that what we feed out to the video is then a blank, and that's how it blanks certain portions of the video, and we'll see that in action in a few minutes. So I've got all this in place now, I've been testing it to see if it works, and so what we'll do now is we'll power up the board, have a look at how that works once we put it into action. And before we do that, I'll show you what signals are present on this IC that I popped out, so you can see what I mean by it being responsible for action in certain things such as key presses. So I'll power up the system, so that's the monitor and the board. Currently now the board is drawing about 900 milliamps. Okay, if we look on the scope, I'll look at pin 1 on this IC, and I'll effectively press one of the buttons by shorting out its connection, and we'll see that there is a momentary signal on that pin. If we go to the next pin on the IC, again there's another signal. And what these signals are doing that are funneling into this IC is whenever there's an action such as data coming in from the serial system or from the keyboard, this IC is responsible for triggering the action to insert it into memory or to update the cursor position, because each time we press the key, of course, or each time we get incoming data, then the cursor position has to be incremented. And so that's what this IC is doing. Now, because it's not there, it means that those actions won't be performed. I won't fit it in this video, we'll come back to that in the next one. What I'll do now is I'll reposition the camera so that you can see the monitor screen, and we'll see what the display looks like now. If you saw the previous video, it was very messy, and what I'll do is I'll switch the video blanking off when I move the camera, so you can see what it looks like without the circuits that I've just been getting running in place, and then I'll switch the blanking on and you'll see the difference that it makes. Okay, so looking at the display, you can see we now have a cursor, which is obviously a big step forward. No keys fitted, of course, no RAM, so we can't display text as such. But what I can do is I can fool the unit into thinking that the key's been pressed. So I'll do that now. And you'll see the cursor advances across the screen. Jumped a few spaces because I'm just using a piece of wire to short out a connection, and also there's a bit of noise and bounce on that, so it moved a few characters, but you can see it moved quite a long way across the screen. What I'm going to do now is flick a switch to select the alternate ROM set that does not have the blanking character. And what this will do is when we get to the end of the line and we start displaying the contents of the ROM, you'll see what the display looks like without the blanking. So I'll just do that now. All I'm doing effectively is pressing keys, or at least fooling the system into thinking that's what I'm doing. And so you can see we've now got what looks like a total mess on the screen. and this is because the blanking characters that it uses for blanking the display for various purposes, as for reading the RAM, retrace, this sort of thing, is not present. What I'll do now is I'll select the character set in the ROM that does have the proper blanking character, and you can see that now we're getting a proper formatted display. Jumping about a bit, and it's distorted because this is not the right monitor for this, and it's not too happy at these frequencies, but I'm hoping you can see it's now a very nice clear representation of all uppercase A's. Okay, also we can see the cursor is present on the display as well. So we've got all A's cursor showing the inverted A. Okay, I'll switch it from 24 to 12 line mode, and you can see that it's now displaying quite happily in 12 line mode. All it does for 12 line mode is it just skips every other line, but you can see that that series of counters is working properly as well. We'll switch back to 24 line mode, and you can see it's quite happy in that mode as well. So now we've got the blanking in place, we've got the cursor generation in place, the display is looking as it should. If this was the proper display for this device, we'd get a properly formatted, nice, neat and tidy display. So it's looking extremely promising. We're reading the data correctly from the ROM, the serial shift registers are working, the cursor counters are working, the screen counters are working, the memory handling blanking is working, retrace blanking is working. So a very large proportion of the system is now up and running, and you can see it's given us quite a nice display. So the next step is to refit the IC that I popped out and see if the board as a whole will now work in its automated mode, and if it will complete these steps without me having to fall into doing it. There's a lot more tedious testing, so I won't video that, but hopefully you can see that I'm making progress on this, and it's looking quite promising so far. Assuming it all works when I pop that IC back in, then the next step will of course be to fit the RAM and see if we can start putting actual character values into memory, and see if we can display real text on the screen rather than just a series of static values. The reason it's showing in uppercase A's, by the way, is because the values being fed into the character ROM are whatever happen to be in the latches, and in every location apart from the blanking location we've got the uppercase A character, so that's why it's just showing A's all the time. Obviously if we had the proper character set, then in theory when the correct value is selected from the RAM to be fed into the ROM, then we should get the proper text appearing on the screen. Okay, so that's it for this video. In the next one, as I say, I'll look at possibly getting as far as fitting the RAM. Any comments are welcome.